Okay, so what I was getting at before I was interrupted by my family is that multiplicity can be explained by what's called the n+1 rule. So a very important rule for us moving forward in this class. It helps us understand where a singlet, a doublet, a triplet, so on and so forth come from. So let's take a look at where these types of splitting patterns come from. It says here that multiplicity results from the magnetic effects that protons have on each other. So protons that are adjacent to each other can have this effect that causes splitting, what we call multiplicity. Take a look at two protons, HA and HB, that are next to each other. All right, so what can happen when we have two protons next to each other like this? Well, protons can align with the magnetic field, an alpha spin state, and they can align against the magnetic field, a beta spin state. And so what happens is that there's actually going to be two different magnetic environments for HA, right? There's going to be a situation where HB is aligned with the magnetic field. So that means it's going to feel a greater magnetic field, which is going to cause deshielding. And then it can also be aligned against the magnetic field, which causes deshielding, or shielding rather. And so since there's two possible magnetic fields that HA can be in, it causes two peaks, right? Two different absorbances. Again, one results from HB being aligned with the magnetic field, and the other one results from the scenario where HB could be aligned against the magnetic field. All right, well, that's when you have only one proton next door. What happens if you have two protons next door? Well, if you have two protons next door, then you don't have two possible scenarios. You end up with three possible environments based off of four different scenarios. Check it out. You could have a situation where both of the HB protons are aligned against the magnetic field, which would cause shielding. You can have a scenario where they're both aligned with the magnetic field, which would cause deshielding. And then you have a scenario where one is up and one is down, but there's two possible ways that that can happen. And so what we should see are three peaks in our signal. So what we call that is a triplet. And the ratio of those peaks should be 1 to 2 to 1. And that, as a matter of fact, is what we see. Therefore, when HA is split by two neighboring protons, we see a triplet. If we go back a slide, what we see is that when HA is split by only one proton, we see a doublet. That is where the n+1 rule comes from. n+1, where the n stands for neighbors. Neighbors. So if you have one neighbor, you add 1. 1 plus 1 gives you 2, and we get a doublet. If you have two neighbors, then you take n+1, where n is 2, and you get 2 plus 1, which equals 3, and that's why we get a triplet. So you can imagine that you're going to get a quartet if you have four neighbors. Let's check it out. Well, look, if you have, sorry, did I say four? If you have three neighbors, 1, 2, 3, then you have n+1 is equal to 3 plus 1, which gives you 4. And that is why we see a quartet when you have a proton that is adjacent to three neighboring protons. So we say it's a quartet, or we say it's split by three protons to give us a quartet. Now, why would that be? It's because there's four possible environments that HA can be in, and they're in a ratio of 1 to 3 to 3 to 1. Right? We have a scenario where all the HB protons are aligned against the field, all of them are aligned with the field, and then we have three possible scenarios where two of them are aligned against, one with, and then three possible scenarios where two are aligned with, and one is aligned against. Give me a thumbs up if you follow me even 60% of the way on multiplicity and the n+1 rule. Three neighbors produces a quartet, two neighbors produces a triplet, one neighbor produces a doublet, and of course, if you had no neighbors, that would be when you get a singlet. All right, so let's take a look here. If you've ever heard of Pascal's triangle, well, the relative intensity of the peak height in the multiplets has to do, or the splitting patterns has to do with Pascal's triangle. I'm not going to quiz you on Pascal's triangle, but you might recognize it here. So by analyzing, and just follow along with me here, by analyzing the splitting pattern of a signal in the proton NMR, you can determine the number of equivalent protons that are next to that proton. Where there are n number of neighboring protons that are chemically equivalent, there's going to be n plus 1 peaks in the signal. So what it's saying here is, if you put it another way, let's say you have a proton, or let's say you have a signal that integrates for 2 protons, and then it's split into a triplet. That means it's going to be next to 2 protons. Let me go back and explain in more detail what I mean. Let's go back and look at a spectrum that we saw earlier on today. Something like this one here, something kind of simple. Well, remember that we said that this signal right here, this quartet, this is a quartet, and we said that the integration told us that it represented a total of 4 protons. And we said that this triplet represented a total of 6 protons. Maybe I'll change this to red. Okay, so let's change this to red. So the triplet, come on, you, there we go. So the triplet, our triplet comes from these protons here. So let's just pick 3 of them. Okay, let's pick these 3 here. 1, 2, 3. Those protons are all chemically equivalent, and they're split by these 2 protons. 2 plus 1 gives you 3, and that's why we get a triplet. If we go over to the quartet, why do we get a quartet for these 2 protons? Because they're split by all 3 of these. 3 plus 1 gives you 4, a quartet. And so that provides you the rationale for the quartet and the triplet in this NMR spectrum. We're going to look at other examples, but there's just kind of a first one to get you going. There's 3 key rules that you have to remember for splitting, right? Organic chemistry oftentimes is about learning a whole bunch of facts and information, and then you kind of got to learn some little, not exceptions, I wouldn't call these exceptions, but just little rules that you have to remember to be able to apply what you've learned. The 3 key rules are this. If you have protons that are chemically equivalent, and chemical equivalence was discussed in section 15.4, they don't split each other. Okay, they can't split each other because they resonate together. The next thing is to split each other, the protons have to be within a 2 or a 3 bond distance. Not all the time, but most of the time in this class, we're going to stick with 3 bond distances. When you have protons that are next to each other or are 2 bonds away, we call that geminal or Gemini, like for twins. So we have 1 bond here, 2nd bond here. So those would be geminal. They're attached to the same carbon. But you can see here that we have 1, 2, 3 bonds away. Then we call them vicinal. Again, we're mostly going to stick to vicinal splitting in this class, but we will talk about geminal splitting a little bit. If you're more than 3 bonds away, so look, we have 1, 2, 3, 4. It's too far away, and we don't see any splitting. Sometimes students will ask me, could you give me an example of number 1? I'll give you an example. The example that's shown in the book would be this. If you had 1,2-dichloroethane, this compound here, these 2 protons and these 2 protons, these 2 protons and these 2 protons are chemically equivalent, right? There's no differentiation between any of them. And so since they're all chemically equivalent, there's no splitting at all. There would just be 1 singlet, no splitting whatsoever when protons are chemically equivalent. And the third rule is that the n+1 rule only applies to protons that are all equivalent. Check this proton that I have in red here. If we look at this one in detail and try to predict what kind of splitting it's going to have. Well, hold on. We have it being split by this proton in blue, I'm going to write here, but it's also split by this proton here that I'm going to write in black. Okay, so you might think n+1, 2 protons that are 3 bonds away. Therefore, 2 plus 1 gives me 3. So this should give me a triplet. You might think that would give you a triplet, but in fact, it doesn't. Okay, it doesn't give you a triplet. Now, if you're thinking, well, why would that be? It's because the proton in black and the proton in blue are not chemically equivalent. They're not identical. And since they're not identical, they're going to have different effects on, or different splitting frequencies or coupling constants, which I'm going to get at in a second. And so this one is going to split it into two, and this one's going to split it into two. And what we actually get is a doublet of doublets. So I'll talk about that more later on in this section. So the degree to which a neighboring proton is going to couple its neighbor, we have a name for that. We call it the coupling constant, or the J value. Okay, so the capital letter J, the J value, and the coupling constant mean the exact same thing. There's only a couple of things, no pun intended, that I need you to know about the coupling constant, or the J value. All right. The first thing is this, is that when protons split each other, they have the same coupling constant. If you're like, well, what the hell is the coupling constant, Mr. Dion? What it means is if you measure the distance between successive peaks in a signal, okay, in protons that split each other, the distance between all the peaks is identical. So we would call this JAB, the coupling constant for protons A and B. If these protons are splitting each other, the distance, that those little red arrows that I have that are horizontal, are going to be identical, right? And they're measured in hertz. Okay, so the coupling constant frequency is identical when protons split each other. Why are the protons in blue a quartet? Because they're split by 3 protons. 3 plus 1 gives you 4. Why are the protons in red or pink or fuchsia, whatever it is, why is that a triplet? Because they're split by 2 protons. 2 plus 1 gives you 3. But how do we know that these are splitting each other? It's because the distance, or the coupling constants, are identical. Let's take a look at the 2 spectra here for the same compound. This compound here, this ester, this is called, the name isn't really important. We cover ester nomenclature in organic chemistry too. But these 2 spectra are taken of the same molecule. They're both of this molecule here. What it tells you on the slide is that this spectrum was run at 300 megahertz, or run on a 300 megahertz spectrometer, whereas this one was run at a 60 megahertz, on a 60 megahertz spectrometer. So if you've been wondering, what's the difference between, a 60 megahertz and a 300 megahertz, and then you mentioned an 800 megahertz earlier on today, who cares? What would be the difference? Well, the answer is this, is that the higher the field strength instrument you have, the better resolution you're going to get between the peaks. Why? Because the coupling constant is going to be a smaller percentage of the overall frequency available. Remember that the chemical shift measured in reference to TMS, you divide that by the operating frequency of the spectrometer to always end up with the same chemical shift. So what happens is, as you go to a higher field spectrometer, or a higher operating frequency, the reason they cost more is not only the magnets are bigger, but you get better resolution. You have less chance of peaks overlapping. Check it out. In the 60 megahertz, we see that these 2 protons here, which should give you a quartet because they're split by these 3, you can see that they overlap with this singlet right here, right? We have our quartet, which is here, but you can see you have 1, 2, 3, but the 4th peak is buried under the singlet produced by these 2 protons. Whereas in the 300 megahertz spectrum, since each what's the word I'm looking for? Each coupling constant is a smaller percentage of the overall number of hertz available. We don't see the overlap. We see a sharper image. We see a clearer picture. Okay, we don't see any overlap between the quartet and the singlet. If you want me to put it in the simplest possible terms that I could, the easiest way to explain it would be this. Let's say you have, I don't know if any of you have seen an old picture tube TV, like the kind of televisions that were around when I was a kid. But if you were to watch TV on an old picture tube TV and compare it to a high definition TV of today, let's say you put on, a movie. Let's say you put on, I don't know, The Wizard of Oz. Okay, you can watch it on either one. Are you going to be seeing the same movie? Absolutely. You get all the same information. However, you see a much sharper and clearer image. I don't know if that's the best explanation. Maybe I should have picked a more modern movie, but give me a thumbs up if you follow me on the whole idea of multiplicity and how a higher field spectrometer, you have the same coupling constant, but you just get a clearer picture. You get sharper or better resolution. And that's why, you know, the more expensive spectrometers are used in, these, high pressure research groups because they can get, more accurate data, not more accurate data, but clearer pictures, especially when you have protons that have chemical shifts that are similar. All right, a couple more points I want to make about multiplicity are a couple of patterns that are easy, or I shouldn't use the word easy in organic chemistry, but a couple of patterns that are recognizable in organic chemistry. Um, and those are an ethyl group, an isopropyl group, and a tert-butyl group. So let's go over the ethyl group first. Ethyl groups are very common in organic chemistry. We learned the ethyl group way back in chapter 4. And we said that an ethyl group it's got a CH3 next to a CH2. So a methyl next to a methylene. Well, how would you know that you have an ethyl group in a proton NMR spectrum? Well, the way you recognize it is because you're going to get a triplet that integrates for 3 protons, and then a quartet that integrates for 2 protons, right? Because we have these 2 protons being split by these 3. 3 plus 1 gives you 4. And then we have these 3 protons being split by 2. 2 plus 1 gives you 3. And if the coupling constants are identical, then it's a dead giveaway that you probably have an ethyl group. Just because you see a quartet and a triplet, that doesn't necessarily mean you have an ethyl group, because these 2 are not splitting each other. Why do we know where they're not splitting each other? It's because the distance between the peaks is not identical. If you measure the distance between the peaks here, you can see that this is clearly different than the distance between the peaks over here. Therefore, they don't have the same coupling constant. And if they don't have the same coupling constant, they are not splitting each other. All right, so that's an ethyl group. What about a tert-butyl group? A tert-butyl group cannot, the 9 protons of the tert-butyl group, so 1, 2, 3, 4, 5, 6, 7, 8, 9, since those are attached to a quaternary carbon, this one here, they cannot be split. There are no protons attached to this carbon in blue. Therefore, there's no splitting. Ergo, anytime you see a singlet that integrates for 9 protons exactly, it means you probably have a tert-butyl group. It's not always necessarily going to be, but a lot of the times it will be. And the last one is the isopropyl group, right? Remember I taught you with the isopropyl group that looks like this. We have a CH, and then you have 2 CH3s coming off of it like this. All right, let me just fix this up. So we'll just put, this is attached to something, okay? Well, since we know that there's free rotation around this bond, it means that all 6 of these protons are chemically equivalent. And then we have the methine proton here. Well, the 6, and maybe I should have switched the colors up here, I guess. The 6 methyl protons, okay, are going to integrate for 6 protons, but they're only split by 1. So if you have 6 protons that integrate, 6 protons as your integration, but it's only split into 2, and then you have something that integrates for 1 proton, but is split into 7, right? 1, 2, 3, 4, 5, 6, 7, coming from the 6 protons, 6 plus 1, giving you 7, then that's a dead giveaway that you've got an isopropyl group. So again, what we covered in the last 2 slides are the ethyl. You need to know how to recognize an ethyl, a tert-butyl, and an isopropyl. Those are the 3 that you really have to be fast at recognizing. And I don't mean it's a race or anything, but those are the things that we see all the time in organic chemistry. The next section deals with complex splitting. I'm not going to spend a lot of time on this, and the reason why is because we don't quiz our students on it in detail in this class, and I want to get to a practice problem with you. But complex splitting just results when you have a proton that's split by two different kinds of protons. Let's say we're talking about HB, okay? Both of these protons, what are they split by? They're split by HC. So HC, there's two protons that are HC protons. 2 plus 1 gives you a triplet. So these two should cause HB to give you a triplet. But then you have three HA protons neighboring it. 3 plus 1 gives you 4, so that should give you a quartet. So what is it? Is it a triplet or is it a quartet? Well, it depends on the value of the coupling constant. If the coupling of A and B is bigger than the coupling of B and C, then you're going to have a quartet of triplets like this. So you see that you have 4 kind of signals here, 1, 2, 3, 4, and they're all little triplets. Whereas if it's the opposite, if the coupling constant of this is bigger than the coupling constant here, so if JBC is bigger than JAB, then you're going to get a triplet of quartets, which would look kind of like this here. However, there's a third scenario, which is if they're similar to each other, then they're so close that you really can't make anything out. And then you end up with a multiplet. So that's where multiplets come from. Okay, and they're very difficult to, determine what's going on. So if you're wondering, oh my goodness, I thought the n+1 rule was hard enough. Well, here's the good news, you guys. In Chemistry 3101, what we're going to assume most of the time is we'll assume that in a scenario like this, that JAB is going to be equal or very close to JBC. So what that would mean is if you were looking at the splitting of this, you'd say that HB is split by 1, 2, 3, 4, 5 protons. N plus 1 is equal to 5 plus 1, which gives you 6. And we will say that HB would give you a sextet. All right. And again, that's something that we do in Chemistry 3101. If you look at more advanced courses on NMR, they look at all kinds of complex splittings, but we're not going to spend a lot of time on that in this class. So what are some other scenarios that you have to be aware of besides the n+1 rule? We saw how it applied to an ethyl, an isopropyl, and a tert-butyl. Then we took a look at complex splitting. I said, we're not really going to worry about complex splitting a lot. We're going to assume that coupling constants are equal when we run into a scenario like we just saw. Well, there's a couple of other little things I need you to know before we can continue and practice looking at multiplicities. And that is, if you have a hydrogen in an alcohol, usually don't get split, okay? So if you look at ethanol in detail, if we draw the Lewis structure, we have 2 carbons, then we have the oxygen, the hydrogen, right, like this. And you might think, well, hold on, shouldn't the hydrogen attach to the oxygen? Shouldn't this hydrogen be split? Look, it's only 1, 2, 3 bonds away from these 2 protons, so it's next to 2 neighbors. 2 plus 1 gives me 3. That should give me a triplet, no? Well, the answer is we get no splitting for that hydrogen. It actually just shows up as a singlet with an integration of 1 in this case. The other proton split, we see the quartet. We see the quartet for these 2 protons, and we see the triplet for these 3 protons here. But again, that proton on the hydroxyl is not split. Okay, no splitting. Well, why is that? It's because of something called hydrogen exchange. Let's take a look here. It says the hydroxyl proton and other labile exchangeable protons undergo a rapid exchange with trace amounts of acid. Put in the simplest possible terms, if you have an alcohol in your molecule, even if you have the tiniest bit of acid in your sample, and I mean tiniest bit, it's going to keep doing this mechanism where this proton is going to get swapped out for a proton in the acid, and then it's going to go back and forth and back and forth. Notice that everything here is in equilibrium. And so since that proton is being exchanged between the red and the blue, it happens so fast, it's like a camera. it's like it's the shutter speed is slower than the actual speed of the exchange. And so it's happening so fast that you can't see any splitting. And it happens so fast that it causes this shielding and deshielding effect. And so the proton that comes from the alcohol usually gets broadened because it's so shielded and deshielded so fast. And that's why in this case, it's not really broadened at all in this spectrum, but oftentimes it'll kind of give you something that's a little bit broad like that. And I'll show you some examples of that as we move forward. But what I want to do right now is park it here on this practice problem and see if we can determine some multiplicities for some protons in here in these two molecules. It says for each of these compounds, determine the multiplicity of each signal in the expected proton NMR spectrum. So let's start with the one on the left, and I'm going to ask you guys for some feedback here. If we start with this guy here, and we'll start with these three protons. We'll start with